So far, we've already covered really confusing circuits, really lame circuits, and then in this one, we're actually going to cover lame and confusing circuits, and we're going to take it to the next level by covering really lame and confusing circuits. So, just get ready for it. Let's try to remember the potential energy equations for a spring and the kinetic energy equation for the block that might be dangling on said spring. We can say that this would be 1/2 k, and then x, some function of t there, squared. And down here it would be 1/2 mv, again the function of t there, squared. But we're going to relate this to circuits now, because we have this oscillating spring going up and down. How does that relate to circuits? Well, there's this really lame, actually it's not really lame and confusing yet, but it's a lame and confusing circuit, an LC circuit, that's going to have a capacitor and an inductor combining together, and they're literally going to correlate to these two things. So the energy, the electrical energy inside of a capacitor and the magnetic energy inside of an inductor are going to match those equations exactly. So the first part's going to be 1/2 for both of them. The next one, K is going to be equal to 1/C. K equals 1/C. This next one is M, and M actually equals L. Yeah, in different SI units, but the same number. So if you get that same number, 1.5 kilograms, 1.5 henries. That's crazy. And then over here we have I of t, just like we had V of t over there. This is squared. And over here we have the Q of t squared. So these two equations will literally be exactly the same, and those numbers will correlate exactly as well. So this is just some crazy stuff. Now there is one more thing that we need to think about for the capacitance. There's actually another equation for the energy in the capacitance, which may come in handy at some point. That would be CV squared over 2. So that may help at some point. And there's also one other thing that we might want to consider before we take a look at anything else, is just the voltages for resistors, inductors, and capacitors. We don't forget how to write out these voltages, for like Kirchhoff loops and stuff. So that would be delta VR max equals I max times R. And then delta VL max equals that equals L times DI over DT, and that could be a maximum there. And then delta VC max equals Q max divided by C. All right, so these are just some equations that are going to help us get ready to understand what's going to happen with these circuits. So let's analyze one of these lame and confusing circuits. These are actually going to be ideal. You can imagine a pendulum swinging back and forth forever because it's never going to run out of steam. So it's interesting because we have two components, the inductor and the capacitor. Now, this stuff is essentially going to be transferring energy back and forth, the electrical energy and the magnetic energy between the capacitor and the inductor. It's going to work like this. First, the capacitor is going to have some charge on it over here, and because the charge is on that side, then we're going to have a current coming out of the capacitor going in this direction, right? So now let's imagine that sort of boost of energy that the capacitor has as a hand that is spinning a wheel. But eventually that hand is going to sort of come off the wheel, and that's essentially the capacitor running out of energy. But since we gave it that push, well, this inductor is going to be spinning. It's going to continue that flow of current, even if the capacitor runs out of energy. Remember, the inductors don't like the change, so they're going to replace that losing the current decreasing, and they're going to push that current through here. So we'll get that current that will continue in this direction. However, in order to get that current, we had to induce the voltage on the inductor. So now the inductor will have some voltage here, and that's essentially how you get that current in there until the inductor basically stops spinning and all the magnetic energy has been transferred into the capacitor at this point. So now what the thing is, though, the current going this direction charged the capacitor from this side. So now that the capacitor is filled up with electrical energy, and well, this whole process will restart. It'll shoot the current this direction again, sort of giving that giving that inductor another spin of the wheel, and it'll spin again and sort of run out of steam essentially. But it'll push the current again this direction because you know, eventually this will run out of current, and then this will essentially replace that current that's being lost over there. And in order to do that, it requires a induced EMF, so we need that right there, and essentially this will complete the cycle. So it goes in this counterclockwise direction here. So that is that's the cycle of the LC circuit and the oscillations. So we can describe these oscillations between the charge and the current with a couple of equations. We'll say Q of t equals Q max times the cosine of WT plus the phase angle here. And that's going to look exactly the same as the x of t function that we used to have in the simple harmonic motion. So that one's should be pretty familiar. And then we also have the I of t function, which is actually going to be the derivative of this thing. So it's going to be W Q max and then sine of WT minus the phase angle. I've simplified this by one step or so, but the idea is in here, instead of the Imax, you could replace this with Imax, but Imax equals WQM. So that's a cool little thing you can kind of interchange there. And then here it's the minus the phase angle, or here's the plus phase angle. So what that looks like is these things are not going to be doing the exact same thing, of course. We can sort of quickly graph this out a little bit. I'll do one period of the cosine graph will look something like this. And then the sine graph will look, this is a negative sine graph really, it'll look something more like that. So you can see that this is at 0 when that's at maximum, and that this is at 0 when this is at the lowest point, the negative, the maximum negative. So like these things are not really doing the same things, they're sort of going back and forth like that. And in an ideal world, this stuff will continue on forever and ever. We can call that W res. That's going to be resonant frequency, when this stuff will just continue forever and never stop. Well, let's try to jot down some key equations. First, we got this omega, which is the angular frequency. That's just going to be equal to 2 pi times the regular frequency. Now, in this situation, in the LC, in the ideal situation, we have the oscillations continuing forever and at the maximum peaks and stuff. We'll call that resonant frequency. So that will be 1 divided by the square root of LC. This is like the ideal situation. Things will keep going forever. And now this is also where you get the strongest amplitudes. Okay, and so we can imagine sort of tuning the radio. So I'll write that right here. So tune your radio. And when we tune your radio, you're going to use a knob to try to find whatever frequency is out there already. So imagine the perfect frequency out there. You're going to try to find it. You're going to need to use a driving frequency. So that would be the WD there. This is your driving frequency. Usually this is going to be given, but you can sort of twist that and try to find the correct frequency and tune your radio to the best sounding station, to the highest amplitudes you'll be able to find. And the last thing we might want to consider is also the period. So period would be 2 pi divided by W. And well, again, so it depends whether you're operating at this. If you're operating at this frequency, you're going to use that one. But if you're trying to find the resonant period, then you would want to use 2 pi square root of LC. Well, so far you might have noticed that we didn't have any resistance. We just had the inductor and the capacitor. And so this stuff was really easy. We essentially got these oscillations to go on forever, and there was no resistance, so that was great. We even had a resonant frequency, so everything was perfectly tuned. However, as soon as we add a resistance to this and make it more like the real world, we're going to get some decaying. These things are not going to go on forever. They're going to eventually stop. So what that's going to kind of more look like is going to be something, I don't know, something like this, where you have bigger ones here, but then they're just going to sort of eventually die away like that. So we have to represent that with some new equations. We'll go ahead and represent the QT as saying it's almost the exact same thing. So we're just going to use QM, the cosine W, but this time I say W prime here. We'll just define what that means in just a second. Then we're going to add another term to this, which is going to be E times negative T over tau. And in this particular case, the time constant is going to be 2L divided by R. So that's cool and all. But we also have the I function as well, which will be more like, you know, we'll have W, QM, and then we'll have the sine W prime T minus the phase angle. And then we'll have the E to the negative T over T right there. So essentially, it's almost the exact same thing as what we had over here, but we're just going to add this E term, here's the time constant, and this omega prime. Now, omega prime is just going to represent when we have the resistor, it's going to dampen the driving frequency. So you'll have omega prime is equal to the square root of, let's say you're trying to operate at this driving frequency, but the problem is you've got a resistor in there, so now it's taking away some of your frequency right there, and so, you know, that's just gonna alter your driving frequency. All right, it's crazy. Now, instead of looking at sine and cosine graphs, we prefer to look at phase diagrams with this kind of setup so that we can see everything at the same time. There's a cool little acronym LIC, the LIC, so you can see that the voltage from the inductor is on the left side. In the middle, you've got the current, and on the right side, you have the voltage from the capacitor. And it's always going to be like this, and no matter what. Now, you can twist this around and stuff to different angles if you wanted to, but it's always going to have that orientation. So you just have to remember that. And then the current and the resistor are going to have the same lineup over here. That's why you have Ohm's law, V equals IR, which is pretty cool. So we like to represent these voltages with some kind of equation. So we'll go ahead and say for all of them, it would be V of T is going to be equal to the generator EMF that we're running at, and sine of WT. Now, we need a generator because of this decay. So, like, you know, if we're operating a generator right here at resonant frequency, then that's really nice, because it's gonna help us, you know, make things really simple. But let's if we could do a lot of crazy things with this generator, and we can push this around to different frequencies. Remember, we're trying to tune the radio, right? So depending on where we are, we're gonna get some different stuff. But this equation should hold true. The problem is that Emax might change. So depending on where it is, a resonance is going to be Emax. But if it's not, then we have to alter that E maximum and change it to some other value. So we could say that it'd be the R max squared plus, this would be VL max minus VC max squared. And so as you can see, if this stuff were to cancel out and go to 0, then you could square root of the R max squared, and then E max would just be equal to the R max, which is nice. But as soon as you start playing around with adding like inductances and capacitors here and there, you're going to start to change this V max. This is going to shift to other directions. So what you'll get is something like this. You might have the E being in this direction, right over here. Or you could also have the E, you know, being in this direction, you know, over here. And the funny thing is that we measure the angles, the phase angles, from where we are here. So if this is the generator here, and we have a positive phase angle, then the current's over here. So the current is like leading the generator, and that's why we have a positive angle. But if we're over here and this is now the Emax, then we're going to go backwards essentially, and so we'll have a negative phase angle. And so that's because the current is behind the generator. If they were both in the same place right here, then you would have the phase angle being equal to 0. So that's nice. And then of course you'll notice, like, yeah, if it's over here, like, if this was twisted there, it'd be higher, but you're kind of getting the time, like you're getting the sine value over here for that generator. So
you know, that's just kind of, it's not the maximum right there. Now, the reason this equation works is, look over here. If you were to try to do the Pythagorean theorem of this, you would need to use this length right here, which is VR, and then you need to use this length right here, which we will actually define this length as VL minus VC. And it doesn't matter whether you're on the right or the left side, it's always going to be that. It's always VL minus VC. VL minus VC. And then you kind of use this side, which is the VR, and then that squared, and so you'll be able to get the Emax up there. And this is really the component that's going to matter, but this is why you kind of have VL minus VC on either side. Now I want to point out that these EMFs are created by a generator that is sort of holding the frequency at a particular point in order for us to continue having the oscillations over time. Otherwise, this is just going to decay. If we didn't have the generator, it would just decay down to 0. Because we have that, then it's going to continue going. And over here, this is no longer going to represent the maximum on the y-axis because the maximums are going to be sticking out in this direction. So you need to get the time function, time varying version along the y-axis. And so in order to get the maximum, you kind of have to twist this that direction. So we also have a time varying function for the E, and we can say that it's going to be VR of t plus VL t plus VC of t. And we can see that from this chart right here. Even if we were to look at this particular angle, this corner here, the VL and the VC are going to be on this x-axis, so they're just going to go away to 0. And so the only thing that matters is the time varying of R, which is up there. And you can see how the time varying of R is equal to the time varying of that. It just happens to be the correct point, so that's the VR max as well. But yeah, so this equation will hold true. And then there's a couple more that we can use. One is going to be E max equals Z times I max. That would be this one. And Z is going to be impedance. So Z equals the square root of R squared plus XL minus XC squared. We haven't actually defined those yet. Well, now let's take a look at if we can represent the voltages of these things specifically. We'll be able to use a sort of variation on Ohm's law. Well, for the resistance maximum, we can actually just use Ohm's law still, because it's going to be IM times R. So this is going to work. But for the VL max, we're going to say that this one is IM times XL. And XL is actually equal to WL. And that's what this is going to be right here. And for the voltage across the capacitor maximum, that's just going to be equal to IMXC. And XC is equal to 1 divided by WC. So these are the equations that you can use to find the voltages across these particular components. Well, let's take another look at this phase angle that we have right here. So we'll say that the phase angle phi is equal to the arctan of XL minus XC divided by R. And we'll call this the phase angle. A few important consequences will happen from that. You might get resonance if XL equals XC, and that would be when these things go away and that thing's just the square root of R equals Z, and these things go away and the square root of that, VR equals Emax, so that's kind of nice. This is when you have a phase angle equal to 0. And for the next thing, you might have capacitive load. If the phase angle is positive on this side, you have XL being less than XC. If XC is greater on this side, you're getting leaning towards this side, you're going to get a positive angle over here, and you're going to get a capacitive load. So it's a positive angle. And if you have an inductive load that's going to swing to the other side, the EMF is going to be on this side, you're going to have mainly a lot of induction, not very much capacitive. So you know, XL is greater than XC on this side, you'll have a negative phase angle. So let's review some power equations now. We got power dissipated. Now, if you have a resistor, then you can use these equations. You could say that the P average is going to be equal to the IRMS squared times the resistance, which is equal to the EMF RMS squared over R. These RMS situations, IRMS is equal to Imax divided by the square root of 2. This really only happens because when you try to do the average of a sine equation, you'll get 0. So you have to square that. So now everything's positive, and you take the average of that, and now you'll get like, you actually get the average. So that's why you kind of have this. You have to square it, and then you can take the average. So this guy is kind of weird. But you also have ERMS equals Emax divided by square root of 2. And this is important. ERMS equals IRMS times Z. Okay, and this is where you're going to find your XLs and your XC. So this is for power dissipated when you have a resistor. We have the power dissipated here through the resistors from the circuit, usually thermal energy dissipation. But if you're trying to supply this circuit with power, then you have this equation. You can use the P average equals the ERMS times the IRMS times the cosine of this phi, which is actually the phase angle. But cosine of phi is equal to R divided by Z. We call this the power factor. This thing is the power factor. And this thing is the phase angle. So ideally, the power supplied, if it's a really efficient circuit, then you know we wouldn't have any Z. This thing would just be R over R. You'd have a one factor. That comes back to this thing. Comes back to the resonance. That's an ideal situation. An unideal situation is when you start having these things out of balance and you have to start calculating things. One last thing we're going to cover is the transmission. So let's say you had a whole bunch of coils here and just a couple of coils there. What would happen is this thing would have more voltage and this thing would have less voltage. So depending on whether you want to go from like a higher voltage to a lower voltage system, you could step down this direction. If you want to go from a lower to a higher voltage, you could step up this direction. And in order for that to work out mathematically, you would have to start calculating the voltage in the secondary is equal to the voltage in the primary times the number of coils in the secondary divided by the number of coils in the first one. And you could also calculate the current in the secondary equal to the current in the primary, and then the number of coils in the primary divided by the number of coils in the secondary. And there's a few more things you want to remember. I equals V over R. This is like the 4th time we've written this equation. But sometimes it's hard to remember that one because they're like written in different ways. Emax equals Z Imax. That's the same equation. ERMS, that's the same equation. And that is all this. It's all 4 different ways to write the exact same equation. They all mean slightly different things. And sometimes it can be pretty confusing. But anyway, we have P average is equal to VRMS times IRMS. And lastly, some vocab words. Let's say we see the word amplitude. What that's really meaning is the maximum. So, you know, Imax. That's the amplitude of the current. Let's say we were looking at omega. We would call this a couple different things. We could call it angular speed. We could call it angular frequency. But this is in radians per second. And for these V of t's, we'll call those things voltage functions. So just some ideas, a couple different words to remember these things.